All right, in this video, what we're going to do is start proving some limit statements using those precise definitions of limits that we've built before. We have two different definitions of limits, one with epsilons and deltas where we measure these distances and we say if you're within this certain distance of something, that means you're close to it. And one with open intervals that says if you're within this same interval with that thing, you're close to it. We're going to look at two different limit statements for these linear functions. They're going to be really easy limits, and we're going to prove those limits. But most of the work is going to be right here in the setup part. Once we set up the proofs themselves will just fall into place pretty nicely. We'll do this twice, one example, but we'll do one for each definition. And then what we'll do is take a look at another example where we look at a different function that will hopefully, this example will be some nice motivation for explaining why I like the open interval version of the definition of a limit. So here we go. We're going to take a look at some epsilons and deltas, the analysis approach. Here's our limit. This is a real easy one. This linear function is no problem. We just evaluate this function at 3, right? So this is just 6 minus 4, 2. No issues there. Our limit is 2. We should believe that. But what we're going to do is we're going to prove that that limit is 2. And to do that, we need to show that for every epsilon greater than 0, there's a corresponding delta that's greater than 0, where when f of x minus L is within this, or sorry, where f of x minus L is within this epsilon inequality, when x and 3 are within this delta inequality. Okay, so what we're going to do is work with this one first. This is f of x minus L, right? And we're going to say this is really the absolute value of 2x minus 6 less than epsilon, right? And what we want to do is we want to connect this x minus a inequality, right? The x minus 3 inequality less than delta. You should notice that there's a connection here. 2x minus 6 and x minus 3 are related to each other. One of them is just a scaled version of the other. So what we can do is say 2x minus 6 is really 2 times x minus 3. Oops, I need a parenthesis there first. There we go. And then when we multiply these things, we can just multiply the absolute values. The absolute value of 2 times the absolute value of x minus 3 then is less than epsilon. And then hopefully we can solve this for the absolute value of x minus 3, and we'll get the absolute value of x minus 3 is less than epsilon over 2. What we're going to do is we're going to use delta equal to epsilon over 2. What this means is that for anybody's arbitrary standard of closeness in the y values, that epsilon value, we can always find a delta. This is like a rule that says if you give me epsilon, I can find a corresponding delta. And then we'll be able to put this all together to show that this proof is going to work. So let me show you how to do that. So again, we should be able to say that if delta equals epsilon over 2, then when 0 is less than the absolute value of x minus 3 is less than delta, we get that f of x minus 2 is less than epsilon in absolute values. So let's work on the proof. We're going to start with the assumption that we have these x values that are within a delta distance of 3, right? And we're going to use delta equal to epsilon over 2 to show that our y values are within this epsilon distance of 2. So here's the proof. Let epsilon greater than 0 be given and assume that 0 is less than the absolute value of x minus 3 is less than delta for delta equals epsilon over 2. This is what I mean by this proof is kind of plug and play. Whatever you find for the relationship between delta and epsilon, you'll just plug in here. So this first line is pretty much going to be always the same, except that's going to change. And like obviously this number will change because x might be approaching a different thing, right? We want to show then that when we use this function, 2x minus 4, the absolute value of f of x minus 2 is less than epsilon for all x such that we're in this delta distance of 3. So I'm just redoing the algebra work that we did earlier, right? I'm looking at this absolute value of f of x minus 2. But now what I'm going to do is I'm going to say, well, this part here, the absolute value of x minus 3 is less than delta, right? And we know what delta is. So we're going to say the absolute value of x minus 3 is really less than epsilon over 2. So that's what I'm saying here. So if the absolute value of f of x minus 2 is equal to 2 times the absolute value of x minus 3, that's what we've shown here, then we'll say that that's less than 2 times epsilon over 2. Because remember, this was less than delta. And hey, look at that. 2 times epsilon over 2 is just epsilon. So that means that the absolute value of f of x minus 2 is less than epsilon. And that's what we wanted to show. So that means that this limit is equal to 2, just like we said it was. End of proof. That's a pretty algebraic proof. We end up just manipulating the epsilons and deltas and doing some factoring and stuff like that. For linear functions, what you're going to notice is that this works out pretty easily every time. You'll be able to find a nice relationship for this coefficient here. That coefficient is really the slope of the line. Think about why that might make sense. Really, it's the absolute value of the slope, right? But that might be an interesting connection to make. So these proofs end up not being too bad once you have this scratch work. That's the really important part, finding that connection between deltas and epsilons. Now, I like this topology approach. We'll see why in a second. But first, let's just go through that same limit proof with the topology approach. I'm going to just draw this thing real quick. Here's our linear function. Looks something like this. And we're going to go ahead and look at the x value of 3. And we've got this corresponding y value, but we don't really care about the point itself. And this is, what's that, 2? That's what we said? Yeah. Cool. All right, what we're going to do is we're going to take a look at some intervals. One from P up to Q, and one from C to D. And what we're going to do is we're just going to trace these values back. And we're going to say, all right, if P and Q are the y values, we need to find what x values we need to plug into our function to get those. Now, this is pretty easy to do. We just set P equal to the y value, which is 2x minus 4. And that means that x is equal to P plus 4 over 2. So that's what this x value is. Or we're saying the beginning of our interval, C. Similarly, we can do the same thing with Q. Oops, this is 2x plus 4. And that gives us the same kind of thing. The x value that we're looking for is, oops, this is supposed to be a minus. There we go. Q plus 4 over 2. So here we'll say D is going to be Q plus 4 over 2. So the interval that we're going to use for C and D is really going to be P plus 4 over 2, comma, Q plus 4 over 2. And that interval of x values will give us this interval of y values. We'll see that in a second. So again, we're going to show that if x is in this interval that we found, the P plus 4 over 2 to Q plus 4 over 2, that means that the y values have to be within P and Q. So we're going to start with this assumption that CD interval, it's the one that we found. And we're going to say that PQ is some interval that has to contain 2. And then we're going to show that this CD interval does contain 3. And that for any of the x values in that interval, the y values will be within P and Q. This comes in 2 parts. So here are all of our assumptions. The 2 parts are pretty easy. You notice I'm starting with 2 being in this interval, P to Q. I'm saying 2 is somewhere in between P and Q. And then I can go ahead and just add 4 to both sides and divide by 2. And you'll notice that means that 3 is in the interval that we claimed was CD. So we can see then that 3 is in C to D. No problem. This is the really important part, though. We're going to say that if x is within C and D, so this means x is in CD, we have to show then that y, f of x, really, is within P and Q. And that's pretty easy to do. Multiply everything by 2, subtract 4, and look at this. This is f of x. That means it's within P and Q. So we can also say that f of x is within P and Q, and so our limit is 2, just like we said. End of proof. Not too bad. Again, you'll notice that this is pretty much plug and play. Once you have these values, those are the things that you do, those are the intervals that you set up, everything works out nicely. So what's the difference? We have these 2 different versions of proofs, these 2 different versions of the definitions. Why do we really have these? Well, part of it is that they have some different focuses, right? One of them is on this idea of distances, and one of them focuses on open intervals. And so we can view limits through these different lenses. And each of these lenses might give us some kind of slightly different perspectives on things. We won't really notice that in this class, though, because we're not going to go any further with this. You'd notice that if you take some topology classes or analysis classes, you'd see some of these different ideas and lenses that we end up viewing calculus through. What I want to do, though, is show you one more example. And I'm going to show you that when we compare these definitions, some of them end up being really, really difficult to do, and some of them end up being not that difficult to do. So let's take a look at this example. Hopefully you can see that this limit is pretty easy, right? We know that the cube root function is continuous everywhere, and so that means that you can just evaluate that function at 8 to get the limit. So there we go. We'll say the cube root function as x approaches 8 is going to approach 2. Let's prove this using the epsilon delta definition of a limit. So what we need to do is set up these absolute values, right? The absolute value of f of x minus L is less than epsilon, so that's the absolute value of the cube root of x minus 2. And we have to connect this with this. The absolute value of x minus a is less than delta. So we're specifically looking for x minus 8 to be less than delta. What we'll notice is that we can hopefully see that there's a connection, right? It's just this cubing connection, but that doesn't work out nicely. If we cubed both sides of this inequality, we would get the absolute value of the cube root of x minus 2 times the absolute value of the cube root of x minus 2 times the absolute value of the cube root of x minus 2, and we'd have to do all this distributive property on there, and that would end up being really, really terrible. So algebraically, what we're going to notice is that there's not a very nice connection here. I mean, we can kind of see what it is, right? But we can't actually do the algebra to get there because this cubing or cube rooting doesn't work nicely across sums and differences. In our last example with the linear function, all we did was we pulled out a common factor of 2. That works perfectly across sums and differences. So we can do that really nicely. But here, we're going to get stuck because the distributive property is going to really screw us up. Okay, so hopefully we can see then that it's going to be difficult to find a delta for every epsilon. It's something that you can do, but it's not an easy thing to do. We could probably see it almost, right? You can almost taste it, but we can't actually do it algebraically to connect things. But if we think about open intervals, this becomes super easy because all we're looking for is an interval in the domain and an interval in the range. And so here is our function. We've got this nice cube root function that goes off like this. Here's our x value of 8. Here's our y value of 2. And we have p and q here. And we want to find c and d here. Well, we can just, I got to fix this. I put them in the wrong spot. We can just trace these back through our function, right? This one's going to be way up here, and then we'll have like d up here. And to find these, we'll just, again, solve these equations where we'll say, all right, p is equal to the cube root of x. And now we can just cube things, and that means that x is equal to p cubed. So that's what that is. And same thing, this one is just going to be q cubed. So that's not a very difficult thing to do at all. Here we go. Let's let PQ be an arbitrary interval, including 2, and we can let CD be P cubed, Q cubed. Oh, that's hard to say. Then we want to show that 8 is within this interval, right? And that's pretty easy to do. We can cube everything here, and it'll preserve the inequality. So 8 is within that interval. Perfect. Oh, my alignment got all messed up here. No big deal. And here we can cube root everything, and look at that. F of x is within that interval, just like we wanted. We can see then that 8 is within C and D, and that if for any x value in C and D, we have that the y value, f of x, is within PQ. And so there we go. The limit works. So because you have this really nice connection with intervals, and we can just trace these back and forth through the function, you don't have to worry about the algebra working out here nicely or not. You don't have to worry about the fact that the distributive property is really frustrating to deal with. In an analysis class, you might learn some of the little tricks that you can do to connect these inequalities, but intuitively, this should be enough. All right, that's where we're at. What should we be taking from this? Hopefully just the intuitive idea of what the heck a limit actually is. I think the visual of open intervals is really helpful for that. I'll throw one more video up here where we talk about continuity in the context of these kinds of precise limits. But again, all of this is just so we can get a really good idea of how limits work. We're responsible in the class that this is for just some basics with the epsilon delta definition. So make sure that you understand how distances work, what epsilon and delta represent. They're these distances that are measuring closeness in the x and y direction. If you want to think about that in terms of open intervals or in terms of distances, it probably won't make too much of a difference because we're not going to ask you to prove these limits. This is still introductory first semester calculus. We don't have to be responsible for those kinds of proofs, but it is helpful, I think, to see them. That's all we've got for limits. Again, I'll throw one more video up here where we talk a little bit about continuity. One of my favorite examples of all time is in that video, so hopefully that's enough of a hook for you guys to go watch that. But after that, we're going to start moving towards thinking about the derivative, which is really the star of this semester. The intermediate value theorem, which we've talked about already, or if you're watching these out of order, you'll talk about soon, and the derivative are really the stars of a first semester calculus course. So that's where we're at. That's where we're moving forward to. Hopefully this helps your intuition, but that should be all we're taking from this.